Next, we look at the term constructions of the simply typed lambda calculus. For every type construction, 0, times, plus, and arrow, the simply typed lambda calculus contains two kinds of term constructions. Firstly, an introduction construction. An introduction construction allows to construct terms of its corresponding type. And secondly, an elimination construction, which allows to use a term of that type to construct terms of other types. Thirdly, we have a computation rule. A computation rule explains what happens if an introduction construction is followed by an elimination construction. This sounds very abstract, but it will be more concrete and will be actually not too difficult to understand once we look at a few examples. We will now look at each type construction separately and discuss for each of them these three items. The first construction we look at is the 0. The 0 intuitively should stand for an empty type, a type with no terms. Correspondingly, we do not have an introduction rule. There is no way to construct a term of the empty type from nothing. The elimination rule explains what we can do once we have a term of the empty type. So here, if we assume that we have a term here called x of the empty type, and if we assume that C is any type, then we can form a new type, which I call here lightning of x, which is a term of type C. Since there is no introduction rule, we cannot say anything about what happens when an introduction is followed by an elimination. So there is no computation. The next term construction we look at is the product times. Suppose A and B are types. Then we know that we have a new type, A times B. Now, how do we produce a term of the type A times B? This is what the introduction rule allows us to do. The introduction rule says here that if A is a term of type capital A and B is a term of type capital B, then we can form a new term that we call A comma B, this pair, which is a term of type A times B. That's the introduction construction for times. On the other hand, if we have a term of type A times B, then we can form two new terms called T.1, which is a term of type A, and T.2, which is a term of type B. The computation rule now says that if we start out with two terms A of type A and B of type B, and if we apply first the introduction construction, so we form the pair A comma B, and then apply the first construction, the first elimination construction, what we obtain is the term A that we put into the pair in the first place. If, on the other hand, we form first the pair A comma B and then take out the second component with dot 2, we get the B back that we initially put in. That's the computation rule for the times construction. We now look at the term constructions for the arrow. Suppose again that A and B are two types. Then we know that we can form the type A arrow B. How do we produce a term of type A arrow B? Well, suppose we have a term b of type capital B, which depends on a variable x, which is of type A. Then we can form a new term, lambda x in A B, which has type A arrow B. So we think of lambda x colon A B as a function with an input in A and an output of type B. The elimination rule says that if f is a term of type A arrow B, so think of f as a function from A to B, and we have an element in A in the input type, then f applied to A is a term of type B. And the computation rule says that if B is a term of type capital B, depending on x in A, on a variable, and A is a term of type capital A, then if we first form the function lambda x in A B applied to A, then this reduces or transforms to B, where we replace the variable x by A everywhere. So I repeat, B, this expression here, B x colon equals A, means replace all the occurrences of x by A in B. This is the computation rule for the arrow, for the function type. Finally, we have term constructions for plus. Suppose A and B are two types, then we can form a new type called A plus B. How do we form terms of type A plus B? Well, there are two options. If we have a term A of type A, then we can form the term in left of A, for which is a term of type A plus B. And if we have a term of type B, then we can form the term in right of B, which is a term of type A plus B again. So intuitively, if we have a term of the left component of A plus B, then we can form a new term of A plus B, which sees this term A of the left component as an element in A plus B. And if we have a term of the right component B, then we can also include this term B. We can view it as an element of A plus B in the form in right of B. The elimination rule says that if f is a term of type A arrow C, and if G is a term of type B arrow C, then we can get a function from A plus B into C by applying this construction brackets f, G. And finally, the computation rule says that if we have an element A in A, and a function from A to C, and a function from B to C, and we first apply an introduction rule to this A, the in left construction, and then feed this argument to the function f, G, what we get out is the value of f at A. So this complicated construction simplifies to this simpler term. And if, on the other hand, we plug into this function f, G a B that is a term of type B, then this complicated construction simplifies to G of B. So what does this mean? Intuitively, this function f comma g does a case distinction. If the argument that we feed to this function, actually if it comes from an A, so if it's in left of an element in A, then we apply f, the first function. If on the other hand the argument comes from B, then we apply the function g, the second function. This is the case distinction that this intuitively this construction f comma g does for us. This concludes the term constructions for our simply typed lambda calculus.